Okay. Good morning. So, today we will continue with cross coupling reaction. Cross coupling, but today the discussion would be restricted to the, of course, the heterocyclic compounds. So, while we do so, we have to have certain things in our mind, namely the complications that can arise during the heterocyclic couplings. Okay. What are the possible problems in heterocyclic chemistry when you come from normal aryl chemistry or aliphatic chemistry? The presence of the nitrogen. Presence of nitrogen actually complicates the regioselectivity. So, but cross couplings are inherently regiospecific except Heck reaction, right. So, that means the regiochemistry should be solved at the early stage, when you make the organometallics or when you make the organohalides, triplets, etc. That is number one. Number two, that also ought to be noted the variations of ligands. So, while we proceed, we will see some of the ligands are unique, and I mean in literature maybe there are about 1000 different ligands, but of course, out of which maybe 10 different or 15 different are very useful. So, while we do this exercise of cross coupling in heterocyclic chemistry, we will come across some of these ligands which are very popular. Okay. So, then secondly, rather thirdly, you have to also note the compatibility with the other functional groups. There are many functional groups which could be compatible, which may not be compatible. So, these are the three important things you have to keep it in mind while you choose a particular cross coupling reactions. In the first class, in the last class, we said that the cross coupling could be prioritized like in terms of number of application, etc. This Suzuki first, maybe then next is Negishi, then Heck, and then other special coupling like Kumada and Stille, all these things. Okay. Then you want more coupling that involves carbon nitrogen formation, that is Buchwald coupling. So, these are the things you have to have in mind. When you are given a total synthesis, for example, you have to have available options in hand, and then you have to have the power of choosing one of them in favor of the others. Okay. So, but for simplicity's sake, we talk about today applications of the Heck reactions, Okay. And so, by now all of us know what are the requirements of the Heck reactions, that an olefin, right, an olefin is required, and an alkyl halide or triplets, or I mean any other sort of functional groups, sulfonates also sometimes, and other carbamates, all these things. At the same time, you have to have also just one more thing, that is palladium, most often, and then occasionally we will use nickel, etc. But let us look at one of the indole synthesis. This is the final indole would be, let us say, Bock. This one we make, or rather this one we want to make. So, what should be the starting material? And obvious starting materials in all of these cases are normally a benzenoid. In most of the cross coupling reactions, one of the starting materials could be benzenoid, and in this case you have triplet on one side and chlorine on the other side, right. So, what next? So, now by looking at what you have to see, and there are so many possibilities. First of all, I mean you have to think about all these possibilities. One of the cross, since you have been talking about the continuation of the Heck coupling, so one of the reactions could be Heck coupling, that is perfectly all right. And then what should be the other one? Heck coupling gives you a carbon-carbon single bond. So, what could be the other? That means, what is the other possible reactant? At one point, what you will find that you have to make a carbon nitrogen bond. So, Buchwald coupling could be one of these possibilities. Other possibilities anything like in this case you have triplet. So, it could be I mean any of these coupling reactions, Heck, Suzuki, all these things. Okay. And now, you have to again sequence the two reactions. For example, you have to sequence one of these cross couplings and the Buchwald coupling, which involves formation of a carbon nitrogen bond. Now, between the two, which one is more facile, that we have to understand which one is more facile. Okay. Whatever may be the case, but one thing it is very clear that triplet is more reactive than the corresponding carbon chlorine, that we all know, because reactivity of the triplet is very similar to that of corresponding bromides. So, that way that means this reaction would be okay. If that is so, then anything could be used. In this case, this N-Bock allylamine has been used. N-Bock allylamine has been used, and the catalyst of course is palladium acetate, and what else we need normally, and what is that? Base. Very good. Base I would not mention, because in most cases the bases are used. But also you have to have a sort of a reducing agent, which could be L-phosphine ligands, and in this case DPPF. This is very useful. I do not know why. I mean, I have no idea what is the clue of using this one. Okay. Now, this is diphenyl phosphinoferrocene. Why suddenly ferrocene? I have no idea. If anybody knows, just you can give me the idea why. I mean, of all available, this particular one is useful in many cases. If you use another substitute, any other, the yields are very poor, or the reactions do not go at all. Okay. So, any case, so once you do this, and there is a tricky reactions actually.
That's about the bite angle.
Bite angle.
In DPF there are two phosphine
Right. Phosphine substituents.
And the bite angle is low.
Okay.
And
so, how does it affect this coupling? See, in this case basically what we need, a phosphine ligand is required to make this catalyst soluble and to make the catalyst zero valent, that is it, no other role. Well, there are of course.
Increasing bite angle, also the probability of reactive elimination increases.
By increasing the bite angle,
Probability of reactive elimination increases.
Actually it's not that easy. Any case, okay. Maybe you just if you have a chance to look at the literature, you just look at, okay, and what you will see and what should be, then you will see there is a unique reactions actually. This is Bock. Normally what you see in the Heck reaction, this aryl group is delivered to the less electron deficient carbon, or stellically less hindered. Okay. In this case, and the aryl group has been transferred to the actually more hindered, but yet this is more electropositive carbon. Like just recall the very first reaction, aryl bromide and acrylates. If you do the Heck reactions, aryl group goes to the beta positions, the one that is more electron deficient. So, in this case this is also potentially more electron deficient compared to the terminal one. Okay. And then you have the chlorine. Now, so once you have this, then one can quickly see what is the other thing. Again what you need is, now this is called Buchwald reaction, Buchwald, or sometimes people say Buchwald-Hartwig reaction. What is required again? This is required palladium, in this case palladium acetate, and a base. Normally he uses I do not know why again sodium tertiary butoxide. this is his favorite, Buchwald's favorite base, sodium tertiary butoxide. Like ours is lithium tertiary butoxide. Okay. So, there must be some reason though, maybe it is actually cheaper than lithium possibly. And what else? One more thing, and a ligand, and a ligand is used. Okay. And this in this so once you have these, then so one can quickly write the product is this. So this is just basically NH attacking the chlorine. That's what should be the next one, and the next step is isomerations. All of us can guess this isomeration here should be pretty easy, because aromatization is the driving force, and this is just simply take camphor sulfonic acid and an organic solvent. Camphor sulfonic acid is obviously soluble in organic solvent, so it can be aromatized. So, let me see, this reaction basically gives you the application of the Heck reactions as well as the Buchwald, but point is that if you fix the regiochemistry to begin with, that means ortho disubstitute, there is no other, and then the rest of the things are almost like regio selective, and the reaction is very good. Let me take up one more example, like you want to functionalize pyrrole. So, it is a 5 member Bock, and iodine here on both sides. Now, you see you have a olefinic aldehyde, and once again the conditions are very similar. So, I should write palladium 0, and the combinations are different in different cases, like in this case the base is potassium acetate and all these things. So, results are again are very similar to all other cases, but then by choosing this example, what we would like to show you that these reactions are very useful. So, you have to identify other things, of course, other things are there like solvent, etc., heat, etc. So, but what is the lesson we learn from this? That is what we have to learn. Any idea? Basically, a simple Heck reactions. So, you have it is a double Heck. That means number one, that means the double Heck can be done in the same reaction pot on the same starting material. Okay. Number two, that this aryl group is getting transferred to the less hindered carbon. When you have a let us say small difference in the electronegativity or electrodensity, that the steric effects actually dominates the regiochemical outcome. And what else do you learn from here? Aldehyde. Aromatic aldehydes are very susceptible to Cannizzaro reactions, and then Cannizzaro reactions, oxidation. Benzaldehyde, if you keep it in air, it undergoes oxidation, all kinds of things. That means actually handling with aldehydes is quite tough. So, that means it is basically displaying the mildness of the reactions. That means Heck reactions could be tolerable for, I mean rather could be useful for most of the sensitive functional groups. Ester, aldehyde, cyanide, they do not get reacted during the process. And with this background, let us say one more example we will cite here. This is something sorry. So, it is sort of a benzophenone kind of thing, and ketone, and once again palladium acetate. When palladium acetate means the other combination is of course triphenyl phosphine, and what else is a base, and tetra, in this case tetraethyl ammonium chloride, and of course there is a solvent is required. There is a solvent required. Fine. So, all these recipes are different in recipes are different in different cases. So, and in fact, you have to optimize the reaction conditions from time to time. Okay. Now, what is the product? Cyclization. Why? Because Heck reactions require an olefinic double bond. This is just the yes. What you said is very right. Actually, the product would be, that means 1, 2, 3, 4, 5. So, another 5 member ring would be formed. Another 5 member and fused. But just this is an example where you have participation of these double bond of the arene ring systems. That means, Heck reaction is not restricted to only the olefinic double bond. It could be of a double bond of an aromatic system, it could be double of an heterocyclic systems. Okay. And actually, I am looking for the structure of S-phos. In the previous example, we have used this X-phos. X-phos, well, I do not have it with me. So, maybe we will some other day we will give you. Then this latest actually in the Heck reaction, latest Heck reactions in Heck reactions could be one of these things is a pyrrole synthesis, is a pyrrole. Not, so far we have taken up the examples where the heterocyclic rings could be functionalized, but in this the one that we are now talking about is a pyrrole synthesis using a Heck reactions. It is a very typically rather non-typical reaction, non-typical reactions. What is the reaction? If I write, I will see apparently it is very easy to work, very easy to visualize, and this is a group here, let us say so fluorine here, so pentafluoro, okay, and let us say R up here. Yes, I say phase transfer catalyst. Yes, I mean you can use benzyl diethyl. I mean it all depends on the. I mean many times there is no justification. Many times just we blindly do trial and error. That's it. Okay, and so this is something very interesting reaction actually. Again, palladium. I think I will write palladium 0. The source is palladium acetate and the corresponding triphenyl phosphine or tolulyl phosphine, and then many times we use triethylamine also. All of us know triethylamine also reduce the reduce the palladium 2. Then the common solvent is DMF, DME, all these things, and a certain amount of temperature and a certain degree of temperature is also required. But what do you expect out of these reactions? What is this? Okay, this is the structure. Now, what do you expect? So, in this case, so what is our expectation? Actually, this is very, I mean, this reaction was developed in late 80s and it was published in an obscure journal. Many of you probably do not read at all. There is a journal called Chemistry Letters. How many of you know of? How many of you know of? Okay, who publishes that? Actually, it is published by Japanese chemists. Okay, Chemistry Letters, Chemistry Record, Bulletin of Chemical Society of Japan, then Chem Farm Bull, all these, there are quite a few journals published by Japanese people. And the Chemistry Letters actually also very famous for the Japanese people. like they are, all of us know they are very patriotic, and they try to publish in their own journal first, and any good work like Mukayama aldol condensation was reported first in chemistry letters, then elsewhere. Okay. So, similarly, this reaction was actually published in chemistry letter first, then Bull-Chem Shock Japan, then slowly some tetrahedron, JOC, all these things. Okay. Now, it is a very nice reaction though. I mean, people did not think about it, people did not think about it. It is unusual, unusual. That is, I mean anyway, rather anything can be thought of, but we have a palladium 0, mind it. We have palladium 0 means it will basically undergo the very first step would it undergo oxidative addition, where to add, that is it. That means it adds across the single bond which is weaker or rather weakest, that is very obvious, right, but it was not obvious till Narasaka discovered this, K Narasaka or N Narasaka, Narasaka discovered this. So, it is such a obvious reactions, and all of us know oxygens are more readily available, easily available. You have a ketone, do the oxygenation, functionalize, you get it. That means getting the starting material is so easy. That means, and then you have a nitrogen now, and the construction of nitrogen heterocycles then should be feasible. I mean, all these things are so feasible, so obvious, but most of the time the obvious reactions are not discovered. So, you have to discover these obvious reactions. Okay. And eventually, that means nitrogen and then palladium. I will not write the oxidation state. So, R up here, and what is what you can think of next? Next is quite easy, right? Intramolecular addition. So, 1, 2, 3, 4, 5. So, that means nitrogen add here and palladium add here. Palladium adds here. Okay. So, and palladium, right. So, what next? This all of us know beta hydrogen elimination. No, when I say so, now at advanced level you have to always think in two terms, little bit of the stereochemistry, regiochemistry, all these things you have to keep it in mind. In BSc, okay, oxidative addition, okay, then reductive elimination, those are all perfectly all right. When you are in higher class, you have to say that the oxidative addition, then what? Then actually cis elimination, cis addition across a double bond. When you have an open chain compound, these both the the palladium end and the carbon end would add across the double bond in the cis fashion. Okay, that is fine, first thing, that you have to keep it in mind. Then if there is any cis-trans isomerism in the coordinate complex, etc., there is a possibility. Then when the beta elimination we are talking about, also you have to keep it in mind that reactions proceeds in, I think yesterday I told you told someone that cis elimination takes place. That is a very critical step though. The beta elimination are often cis eliminations. Okay, that means palladium and the hydrogen should be oriented cis. Okay, around this single bond. Now, in this case, the regiochemical problem here, and so this if you have hydrogen on this side, that could be eliminated. But in this particular example, the hydrogen eliminated from the side of the ring. So, you will have nitrogen double bond, this is R, and then you have R up here, and then if you equilibrate with I mean something, any kind of, let us say acid. So, what you will find? You will find a nice 2 substituted pyrrole. Now 2 substituted pyrrole. Okay. So, it is a nice reaction though, I mean it is a pretty general reactions and it is coming up, but this is a very interesting in terms of the chemistry. Why? I mean nowhere even today, I mean we have come across many examples on Heck reactions, but we have never come across a reactions where a rather carbon nitrogen bond is being produced. Okay. That is the uniqueness of this reaction. And one of these latest examples would be just you see here apparently again. So, if this reaction known, then what is the use of doing this then? Someone did this year, not this year or last year I think. Again all these things. Any idea why? Why should, first of all, if someone did this top reaction, why should they do this reaction? Because you see here 1, 2, 3, 4, 5, the interrelationship nitrogen and the double bond 1, 5. Okay. Oh, sorry, I think this is nitrogen here. Now 1, 2, 3, 4, 5. So, I mean chemistry wise it is not at all an advancement, right, but somebody has done it, and then of course, he has published in a very good journal Angumantesivi. So, there must be something then. So, if you see the outcome you will find okay, what would be next intermediate? Next intermediate could be right, this nitrogen gets paradiated, the palladium nitrogen adds on this end, or the palladium adds to the other end. So, here is the palladium, okay. And if you recall what I said, addition is cis. So, that means this is beta, let us say, and this is beta. So, that means there is a hydrogen up here, and this hydrogen should be cis, all of us know why. Maybe tomorrow's viva someone will catch you why this should be cis.
Bicyclic compound trans-ring junction is very strange.
No. Trans is more stable. No, you have to know.
Yeah.
You have to know. This is a very important piece of information that you have to know, because in steroid chemistry A B ring is trans, B C ring is trans, and C D ring is cis. Why? Because cis hydrogens are more stable. Cis hydrogen, this is called cis hydrogen. Cis hydrogen is more stable. Okay, thermodynamically more stable. So, this is one of these. Okay. So, now what next? Beta, no, cis beta elimination. If you remember that, then you will not make any mistake. So, that means palladium on this side, on the cis side there is no hydrogen. So, there are two hydrogens on this side, this cis one will be eliminated. That means what you will get? You will get this bicyclic indole or hydrated indole. So, you will have this product. Okay. So, and these sort of things, this is R here, and then this is R here, the rest of the things are okay. So, what you now are getting now is sort of a bicyclic alkaloid kind of compounds, and then you have a double bond here, remote double bond. You can do all kinds of functionalization, oxidation, all kinds of reactions you can do. Okay. Now, just talk about just a Suzuki reaction. Next most important reactions of course is Suzuki reactions. I think let us say I will straight away go to the exact product that we are trying to target. This product in this case is known as product in this case is known as pyrrolinitrine. That means a structure is having a pyrrole unit here. No, sorry, here this is nitrogen and 3. So, what you will see, this is a okay, this is pyrrole here. Pyrrole here, that means 1, okay, 2, 3. So, 3, 4 disubstituted pyrrole, and the one of the substituent is aromatic, that you can see. I mean, it is a very tough molecule. and this is known as pyrrolinitrene. Okay. So, how do you make it? So many things we can ask ourselves. Okay. Since it is a topic of the, it is a class of cross coupling, so we can just divide this molecule into two aryl groups. So, obviously this one. Once you have this, then you have to find out which one would be the metalloid, which one would be the halogenoid. That means one side you have halogen, other side has the metal. Then you have so many things possible, etc. But since the Suzuki is more Suzuki is expensive, but most reliable. So, that means we can talk about Suzuki then which one, the Suzuki, that means Suzuki, whether we should place boron on the phenyl side or on the pyrrole side. Do you understand what I am saying? I mean, it could, the boron could be placed on the aromatic ring system or the other side, but how do I decide? How do I decide? Okay.
How easy to make the boric acid?
How easy to, right, that is it. Normally the easy accessibility, which one is more easily accessible. The boron means you have to, halogenation is so well studied in case of aromatic chemistry. So, one can make it, right, and okay, maybe we will talk about that little later. Then, but you see here the important feature of this molecule, that the pyrrole is substituted at 3 and 4 positions, but whereas all of us know that pyrroles are susceptible to undergo reactions at 2 and 5. So, how to drive the reaction to 2, 3 and 4, 3 and 4. Okay. One of the tricks that one of the scientists did is basically started with a halogen compound, and which was nicely obtained from just a simple pyrrole. This I will just give you the answer, because this it will take a lot of time if you go back to discuss all these things. Tips, try isopropyl silyl, try isopropyl silyl. Okay. The way one can do is sodium hydride and tips chloride. Okay, that is perfect, all right. What was his discovery? That if you do this reaction with NBS, NBS is an mind it, NBS is a source of radical bromine, but if you do not use heat, if you do not use light, just at room temperature or even below room temperature, it is a ionic bromonium ion, and pyrrole is so reactive, you can actually use in this you carry out the reactions at -78°C. Now question is where it would attack. It is a bromonium ion. So, electronically we would expect this attack at the 2 position, but in this case very interestingly, and the yield is so good in 90% yield and tips. That is the trick. That means the steric crowding of the silyl group has been used to make a regio specifically 3 substituted bromo compound. That is it. That is the trick. Well, then one would say you can use also N-chlorosuccinamide for introducing chlorine, right, because you need a chlorine here. You need a chlorine here. So, how do you do? Obvious choice is N-chlorosuccinamide, but what is the problem? Let us say if the reaction fails, what is the problem? N-chlorosuccinamide. Between the what is the difference between chlorine and bromine? Which one is more oxidizing? NCS. Chlorine is more oxidizing. So, actually it decomposes the whole material. So, that means I mean they were unable to produce this by this one. Okay. So, what they had to do it, you had to convert this bromo into chloride, aromatic bromo into chloride. So, how do you do? Tips. Now, so here something, I mean this such a simple molecule took so many steps actually. How do you do? We have discussed all about. tertiary butyl lithium. So, you get the lithium, then C2Cl6. So, what do you get this? So, that means now you have a 3 substituted pyrrole. But then we need a group here at the 4 position. Okay. In this case, the 4 position is substituted with the boron compound, and this was now again NiS. Now, if you put NiS, so you have a chlorine up here and iodine here and tips. And what next? You have to substitute iodine by boron, and once again what is the reaction? This is a borylation reaction. Borylation reaction we have not talked much. There are two. One of the very famous reagent is, I said, no, borylation. Yeah, Grignard you can do. Grignard also then you can do. Now these days people are doing borylation directly by pinnacle boron or dipinnacle boron. Okay. So, then you have a palladium 0, once again palladium 0. You see carbon boron bond also can be made by using palladium 0. So, eventually what you get is this tips and this, and here you will have a boron pinnacle boron. So, this part is all right. So, when you have this part, then other aromatic part should be, this is chlorine, this is nitro, and then this one should be then iodine or bromine, because you have to do a selective coupling. Now, see such a simple aromatic compound, but it gives you lot of pain. Why this is problematic, and what is the why should it be so problematic? You have to identify the right. That means, you have to put all these substituents side by side in contiguous manner. Okay. So, that is quite tough, all of us know. So, then once again, how to circumvent this problem, how to reduce the problem. Again, lithiation, that is one of the modern technique and most regioselective. So, they begin with the prerequisite, and if you do the reactions with LDA at minus 100 degree centigrade, what do you expect? See, LDA reactions is driven by acidity as well as chelation. Okay. In this case, because of the halogen groups here, is highly, the middle one is highly acidic, so it undergoes lithiation. And thus, so if you like organomagnesium compounds, if you treat these lithium compounds with carbon dioxide, so what you will get? Carboxylic acid, fine, that's no problem at all. Okay. So, carboxylic acid. So, carboxylic acid, and this is chlorine and this is bromine. Now, what? Now, we have to convert this carboxylic acid into nitro. How do you do? Simple, right? Hoffman, okay, right. So, but of course, probably they had a bypass. What they did, they I think use what is that, Curtius rearrangement, Curtius or Smith, azide and acid. What is it? What is the name? Smith. Okay, fine. Then Smith, fine. So, if you do the Smith reaction, so you get this amine here, chlorine, and this bromine here. Then subsequently, you can do this oxidation. They have done it with metachlorobenzene, MCPBA. And then these two have been coupled. This boron compounds and these two have been coupled, and the standard reagent radium 0 and a ligand here. In this case, the ligand is S-phos. Previous one was X-phos. Okay, S-phos is something like this. Phosphine here, cyclohexyl, and then you have an aryl ring with 2-methoxy. So, of course, there is a region to be named as S-phos. Why S-phos? There is no sulfur though. This one, this is the ligand they have used for coupling this reaction. Not configuration. This S actually I came to know when one speaker came to our department. He gave a seminar, and he was a Buchwald student. Okay. So, he said this name was given by Buchwald himself, because there is only single phosphorus. So, that is why it is called S-phos. Okay. So, let us take up one more example. I have quite a structure is like this. You have a biphenyl, then one of the phenyls carries 2 methoxy groups and ortho positions, and the other okay, whatever the position is, the other position is dicyclohexyl phosphine. Okay, I have many more examples. So, likewise, Negishi coupling also is pretty useful. I will just give you one example, probably that would suffice to illustrate the superiority of the Negishi coupling. So, here is you see here coumarine, sorry, this is I think I should not write here. I think just keep it in mind. Oh. This 4-bromocoumarine, 1, 2, 3, 4-bromocoumarine can be made, of course, can be converted into the zinc compound. And what is the zinc? The most reactive zinc. Anybody remembers? Zinc compound, activated zinc, the starred zinc, Ricky zinc. Okay, Ricky himself only very recently has done this. Okay, and then do this Negishi coupling with iodoaniline, this palladium acetate again, and the ligand he also used the ligand S-phos, and obvious product. I think these couplings are so well established, and so what you can see, the obvious product is this. Now, you have to understand why actually this reaction is citable or should be studied. What are the lessons we learn from here? Once again, the mildness of these reactions, mildness, all these cross couplings are very mild, right? Because you see, in most cases, if you are handling with an amine, you have to do all kinds of protections, bog, acetate, this thing, that thing, benzyl, benzoyl, all these things, but you do not require any protections of the amino group. That is the advantage, one of these very important advantages. And then if you have a lactone like coumarin is basically a lactone. Lactone would undergo all kinds of reactions. You cannot use sodium hydroxide, you cannot use any kind of strong base, this lactone ring would open up. So, the lactone ring also survives during the conditions. So, that is the advantage, and so this is one of the examples. Let me give you one more, probably Suzuki coupling. This is nothing. Okay, I think I will give you one more. Okay, fine. Let us say you have a pyrrole derivative and now use sodium hydride. So, we know what happens with sodium hydride in the previous case in the silylation reactions, what you see that it would form a sodium salt. Now, if you treat zinc chloride, so what do you expect? A transmetallation will take place. So, that means it should be this in fact this transmetallation is a very low temperature reaction, and once you have this, then let us say you use an bromoarenes here are. So, nothing happens, then you use a palladium reagent. So, in this case I write just palladium 0, and the ligand is very similar to S-phos, The ligand is S-phos is nothing but is a, if you recall, it is a biphenyl with a phosphorus, and it is a cyclohexyl group and a cyclohexyl group. And what are the other thing in S-phos? Methoxy groups, but in this case there is no methoxy, that is it. So, that means you keep on changing ligands here and there, whatever is available around, you just keep on optimizing things here. But then see without ligand nothing happens, just both the reactants sit together and no reaction take place. Then if you put palladium, obviously there is a reaction called Negishi reaction, but question is where does this aryl group go? Well, ring does not break. So, this portion remains as it is, right, and after the workup you will see NH you get. So, what does it mean? That actually the arylation is taking place at a carbon. Now, obviously which carbon between you have to either 2 or 5, So, it is the 5, that is it. So, that means it is very selective and the reaction takes place at 5. So, likewise there are this is pyrrole zinc especially is very useful, and there are so many examples that have been worked out. And what else? So, I think we have come to almost like to an end, and let me give you one more, probably one or two more. I think I have one more example. Which one next? We have talked about Heck, we talked about Suzuki, talked about Negishi, and what we did not talk about then? Stille, and what else? Sonogashira. Fine, I have an example of Sonogashira, but Sonogashira all of us know. Basically, yes, Sonogashira is good, no doubt about it, and it is very useful. So, in heterocyclic chemistry, once you have, and basically all other cross coupling reactions, if you have the right requisite reacting partners, the reaction would take place without much problem. Okay. The one I will give you, I think this is from a Stille coupling reaction. It is a natural product we will be talking about. It is a pyrrole natural product. It is known as mica lazole. It is a marine natural product, and then you have a big carbon chain here. It is a carbon chain containing so more than the carbon number of carbon is more than 16. It is a long carbon chain, and then you have on this side you have an alcohol here. So, how do you make it? First of all, you ought to know that the pyrroles are very reactive. if you keep a bottle of pyrrole for many days, it becomes black, it becomes black, right. It's polymerization, so all kinds of things happens, oxidation, all kinds of things. So, but yet they are found in natural products, but most of the natural products of pyrrole contains an electron withdrawing group. In this case, you have a carbonyl group. So, once you have a carbonyl group, the compound is pretty stable. Any case, our problem is to synthesize this compound, let us say, and synthesize this compound. So, starting point, starting material, okay, this should be your homework for the next class, for Friday. How to make the starting material? How to make the starting material? So, in this case, so as I said before, at the early stage you fix up the regiochemistry, all this problem. So, once you have two different groups in this right position, then rest of the reaction should follow the course of the reactions, and then eventually you will reach the right target. So, once you have a tin, then of course, you know what we are going to do. We are going to do a Stille coupling. So, this is the metalloids. Then now you have to have a halogenoids. What is the halogenoids or halogen containing compound? What would be for a change? You will see that is nice. Now you do not have to have Stille coupling. You do not have to have an olefinic compound. Okay. Even if it is just a simple acyl chloride also would do, that is it, nothing else. Normally, the Stille coupling takes place between the tin and the corresponding halogen compounds, normally iodine, but in this case the acyl chloride is perfect chloride, acyl chloride is perfect chloride. Okay. And so, once you have this, then that is it, nothing else. So, this thing, and in this case the palladium is diphenyl palladium chloride, palladium chloride, then of course there must be ligand, but ligand is not okay, and hydrogen here, aldehyde and See, once again you see aldehyde remains intact, and this O and the acyl chloride. Okay. So, once you, so what next? Reduction. No, I should not say, we have to say selective reduction. So, how do you do selective reductions of this aldehyde to the corresponding alcohol? So, you have ketone, you have aldehyde on very similar position, 2 and 5 means they are very similar position in case of the pyrrole. See, NH is not first of all protected. So, that takes care of these. I mean, Stille coupling is such a mild reaction, so NH does not have to be protected. So, you have nice coupling. Now, you have, this is just a case of the basically selective reduction case. So, just suggest a method, suggest a reagent that would reduce only the aldehyde. You have been learning so many reductions. Huh? Cyanoborohydride, no, cyanoborohydride requires acidic conditions. Huh? What is Redal, by the way? Yes, there is a compound Redal. Actually, at this moment I have forgotten the structure.
So the only methoxy group is.
Oh, I see. Okay, lithium aluminum hydride titrated with anisole something, right?
No, not aromatic, aliphatic methoxy group.
Aliphatic methoxy groups, methanol.
Sir, at the end of the chain there is methoxy group, and before that, when I mean.
Right, the methoxyethane. Maybe, okay. Any case, just look at that. Yes, Redal sometimes used, but I have no idea at the moment. But the one I know, these people have used is something somebody also worked heavily on the reagent from cultivation of science, D.C. Ranu. Originally he was famous for using that reagent, zinc borohydride. Zinc has a stronger affinity towards oxygen, so activates the aldehyde and eventually it gives this. Okay. So, I think I will skip this Sonogashira. I will keep this Sonogashira. So, summary, what is summary? Let us say, what is new about the cross coupling in heterocyclic chemistry? So, basically extension or applications of the cross coupling in heterocyclic chemistry glorify the cross coupling reactions. That means, they are more versatile, they can be used anywhere in the chemistry, that is number 1. And number 2, the most of the cases the reactions are mild reactions. That means, the protections of the groups, especially nitrogen containing group NH2. I did not give you one example where the phenol is there, the reaction does not go. Phenol is acidic. So, that means, all these cross coupling reactions take place in slightly basic mediums, basic or neutral mediums. If carboxylic acid is there, there is a chance the reaction would not take place, that you have to keep it in mind. Third thing is versatile, and fourth thing, what is the fourth thing? Summary. Go back and see and tell me. Okay. Fourth thing is right, that the cyclization of the oxime, I should say Narasaka-Heck reaction. By Narasaka-Heck reaction, that means you can form a carbon nitrogen single bond, that is important. Okay. And lastly, what I did not talk about, I had things that this, if you recall, this Andrew Hamilton also said that. I had an example also that there are molecules you can synthesize by repetitive Heck reactions or Suzuki reactions. Let us say you have a pyrrole, you want to place 4 different substituents on the pyrrole's 2, 3, 4 positions. Okay, you do one Suzuki, then next Suzuki, then next Suzuki, then next Suzuki, you can go on. That means, they are not that susceptible to steric effect, but yet susceptible. That means, if you want to put the 4th one by Suzuki, the yield drastically decreases. That means, to some extent all these Suzuki reactions also, all these reactions are sensitive to steric effects. If you recall, Andrew Hamilton, what did he made? No, polyphenylines. Then at one point he said that the yields, these are not good method because the yields progressively decreases. Okay.